Previously, we learned how vector search and metadata filtering retrieve relevant information from a vector database. Now it's time to level up. In this episode, we'll explore 4 advanced retrieval techniques that make production RAG systems significantly more accurate. The first advanced retrieval technique is query rewriting. Users naturally ask questions in a conversational way, often including background information that isn't useful for retrieval. If we send these raw prompts directly to the vector database, the search may not return the best results. Instead, an LLM first analyzes the user's intent and rewrites the query into a concise, search-optimized version. This rewritten query is then converted into an embedding and searched in the vector database, resulting in much more relevant documents. For example, instead of searching with an entire conversation about planning a vacation, the LLM rewrites it to simply paid leave policy for employees and annual leave entitlement, making the search far more accurate. The second advanced retrieval technique is named entity recognition, or NER. Instead of rewriting the user's query, NER identifies and extracts the key entities that matter, such as organizations, products, people, locations, and dates. For example, when the user asks, "What was Apple's revenue in 2024?" the system extracts 3 entities: organization as Apple, year as 2024, and metric as revenue. These extracted entities are then used to filter the knowledge base, narrowing the search to documents related only to Apple and the year 2024. Once the search space is reduced, vector search is performed on these filter documents to find the most semantically relevant information about Apple's revenue. The third technique is hypothetical document embeddings. Instead of embedding the user's question directly, it first asks an LLM to generate an ideal document that would answer the question. For example, if the user asks, "How do I deploy a fast API application on AWS?" the LLM generates a short document describing the deployment process using Docker, EC2 or ECS, Jinx, HTTPS, and CI/CD pipelines. This generated document is then converted into an embedding and used for vector search instead of the original question. Since the vector database now compares one document with other documents, rather than a question with documents, the semantic match becomes much stronger, resulting in more relevant retrieval. While all the techniques discussed so far improve retrieval before or during vector search, our final technique works after retrieval. It is called re-ranking, where the retrieved documents are re-evaluated and reordered so that the most relevant ones are sent to the language model for answer generation. The vector database typically retrieves the top 20 to 50 candidate documents based on semantic similarity. However, these results are not always in the best order. That's where a more powerful model, such as a cross-encoder or an LLM, comes in. Instead of embedding the query and document separately, it evaluates each query document pair together and assigns a new relevance score. For example, if the user asks, "How do I reset my company VPN password?" the initial retrieval may return several related documents, such as the VPN installation guide, password policy, or troubleshooting guide. The re-ranker then identifies that the VPN password reset procedure is the most relevant document and moves it to the top. Only the highest-ranked documents are finally passed to the language model, resulting in more accurate answers at the cost of only a small amount of additional latency. To summarize, query rewriting optimizes the user query, NER extracts key entities for metadata filtering before vector search, hypothetical document embeddings improves semantic matching, and re-ranking refines the final results. Together, they make RAG retrieval faster, smarter, and more accurate.